welcome back. As promised, we will now get started with some of the patterning techniques. In our previous class, we discussed about the two basic paradigms of patterning at the meso and nano scale. If you can recall, one of them was the so called top down method and the other one was the bottom up or the self assembly methods. In this particular course, we will talk about a third paradigm, which is very close to the bottom up technique of self assembly, but not exactly similar, and which we will term about as the self organization methods. So, this is something that not too many people really discuss, but we would like to sort of place this as the third paradigm. And well, this is actually where the name of the course bridges the two. This type of self organization, we have actually, if you very carefully listen, we have talked about this type of self organization in one of our introductory classes, and this self organization we will talk about essentially is based on the instability of various sorts in ultra thin films. We have I have given you one example, one such example, and that is based on what is known as the duetting. There will be some other settings also, where we will essentially show, or our objective is to show that the self organization or the morphological evolution during the instability of an ultra thin film, particularly we will be talking about the polymer films, and why we will be talking about polymer films and not other generic liquids like water or organic solvents will also, I will make it clear to you in due course of discussion, how this instability itself can sort of manifest as a viable patterning technique. So, we will see what are the forms of instability. One approach, scientific approach, very significant, very important from the standpoint of industry, is to how this instability can be inhibited. So, in order to achieve that, also it is extremely important that you have a complete understanding of the instability process, but what we will show is that these type of destructive instabilities, which sort of leads to rupture or disintegration of a thin film, in many cases it is a spontaneous rupture or spontaneous disintegration, can also be sort of used as a viable patterning technique. But that before that, we will look into the conventional techniques, particularly the top down techniques, and we get started with what we plan to discuss today, that is photolithography. Again, we have introduced you, or I have talked in the initial lectures, that this is one technique on which the microelectronic industry significantly relies on, and the phenomenal growth in the microelectronic industry in the form of faster computers, smaller laptops, high resolution display, large or high capacity memories, pretty much everywhere this particular technique has played a very significant role. So, it is important, I mean, people from electronics background sort of have deeper understanding of this. This is interestingly one technique where lot of research, high end active research goes on, and this is one research area where a lot of findings, or almost every finding, finds industrial application. Frankly speaking, photolithography itself can be one full course covering one entire duration. So, there are lots of nitty-gritty issues, there are a lot of automation, automatic processes that have now been incorporated. So, all these things are there, but we will sort of talk about some very basics, so that you understand what the process is, how it works, and what exactly is done in the microelectronic industry, or how patterning is achieved. And then we will shift gears to the other lithographic techniques or areas where patterning is done, and so which fall and which are more of polymer specific techniques, so which fall under the category of soft lithography. These methods we will talk in rather greater details, including processes like micro contact printing, nano imprint lithography and its variants, capillary force lithography, micro molding in capillaries, etc., etc. But today we will be discussing on photolithography. Okay, so let us get started with what photolithography is. This is a quick sort of recap of what we have already told, that innovation in the field of integrated circuit is the main or photolithography is the main motive force for the tremendous advancement in the field of microelectronics. These are some numbers you may be interested. Transistor was first invented in 1947. The first IC or the integrated circuit was built in 1960. At that time the line width and now I hope you understand what exactly the line width means. It is the width of P or the n type domains was roughly 5 micron. So, first IBM PC was developed in 1981 with a 16 kilobyte memory, sounds childish now, and a 4.77 megahertz clock speed. For a 40 GB DRAM around 1997 it was huge, the line width was 350 nanometer, and as we have talked in one of our previous lectures, the line width is roughly around 30 to 35 nanometer for Core i5 processors of Intel as of 2011. Now, closer is the packing, better is the performance of the circuit, higher number of transistors you can put, so faster other things. So, again here it is more of the same thing, a brief history now pictorially. So, 1971 Intel 4004 microprocessor, 1985 Intel 386 microprocessor, Pentium 2 around 1997, 2006 Core 2, now 2011 we are talking about Core 5. Pretty much the same thing. This is what I was talking about, the line width. So, you now understand that by line width we are talking about the widths of the p type and n type domains. So, each one of the interfaces of the p type domain and n type domain acts as a transistor, and what we have briefly discussed and what we will take up in greater detail, that you create these type of arrays of p and n type domains on a silicon wafer, which is the basic building block for the microelectronic industry as of today, is achieved or can be achieved by the method of photolithography. So, this advancement of how many transistors you can place inexpensively on an integrated circuit has given rise to the now famous, now very famous I would say, Moore's law, which says that the number of transistors that can be placed inexpensively on an integrated circuit doubles approximately every 2 years. So, what it means that this law predicts, or that is how the advancement in the field of microelectronics has gone so far, is that the narrow line width sort of becomes half of what has been achieved in a previous year or in exactly 2 years. So, this is again a pictorial representation of Moore's law. So, it shows, so let us say from 1990 where you had a transistor count of 1 million, it is sort of looking into billions now. There are technical issues also which are coming up as a consequence of this. So, we will discuss some of this. Now, let us look into what photolithography is. This schematic actually captures rather nicely all the significant steps, but I am sure if I show you this it will not make much sense to you. Also we have a sort of a animation which will give you an idea about different steps of photolithography. At this point I will request you to have a look at this one without worrying too much about what is going on. So, the different steps: surface preparation, deposition of the barrier layer, photoresist application, soft bake, mask alignment, exposed to UV, developing, hard bake, etch, resist strip. These are the different steps. I will give you an idea what exactly you want to do. So, we will revisit this sort of animation as well as the schematic later. So, you effectively understand what it is. So, let us look into it from a very simplistic standpoint. All you essentially have is a surface of silicon which is better known, which comes in the form of a wafer. Wafer is a disc like material which can be a few hundred micron to about a millimeter thick. Now, you may also know that silicon is a crystalline material, and it is possible to create silicon with different orientations like 100, 110 or 111. Now, at the very outset I have told you that we will be having a very simple understanding of photolithography. So, we will deliberately avoid a lot of intricate nitty-gritties, and we will just have a gross idea about what is necessary to do. Now, it is, you may also know, or it may be important to note, that silicon has very high surface energy. This is number 1. So, when you create fresh silicon, or if you break silicon at a lattice plane, it exhibits a surface energy something in the range of 420 to 430 millijoule per meter square. Compare this to surface energy of water, which is roughly 72.8 millijoule per meter square for water. So, if I now forget about patterning and everything, and I ask you that if I want to dispense some water on a silicon surface, what is going to happen? Most likely what is going to happen, you are going to see a complete wetting. Okay. This is rather uncorrelated to what we are going to discuss today, but whatever we have discussed in this course so far, based on that, probably this concept should be clear to you now. Now, the problem is, since this has a very high surface energy, it is rather unstable whenever it is exposed to atmosphere. And what happens is, as soon as a silicon freshly prepared silicon is exposed to atmosphere, which contains a lot of oxygen, which is amongst oxygen and nitrogen the more reactive species, there is immediately a surface reaction, or there is an oxidation, or you can say surface oxidation. And what happens is, so if this is your silicon, there is a very thin oxide layer. Or many times it is written as SiOX, because this can be non-stoichiometric oxides also. But important thing to know is that will definitely be an oxide layer, which is known as the native oxide layer. Okay. And typically this has a thickness of 1.5 to 2 nanometer. If you have a good quality ellipsometer, you can measure the thickness. Okay. Now, if you remember what we have discussed, we actually want to create this type of an array of p type and n type domains. What is typically done is that when for a lithography purpose or fabrication of an IC, a silicon wafer is manufactured, typically one type of doping is already given. So, instead of starting off with a bare silicon which is undoped and then try to create some parts or dope some parts with p type and some parts with n type. Now, let me also tell you that we will skip all the details of what exactly is necessary to be done to have a p type doping or an n type doping. We will avoid the chemistry, but we will conceptually understand from an engineer standpoint what processes actually takes place. So, you typically get started with, let us say, a p type doped silicon wafer. So, you have a silicon wafer which is already doped, let us say it is p type doped, and also it has a 1.5 to 2 nanometer thick oxide layer. So, this is where you get started. Now, your essential objective is that if you have, let us say, a p type doped wafer, you would like to create on its surface regular domains of n, so that as we have drawn in the previous slide, you actually have p-n junctions. Okay. So, this is your objective, right. So, what can be done? The best thing to do is you start off with a p type doped wafer, and then somehow cover it or cover parts of it with something, and then expose it to an environment where there is a reaction at the surface and there is n type doping. Right. So, you have to cover parts of the wafer with something. As of now we are talking that to be a something, later we will talk to the details. So, that the n type doping, the chemicals which you are using for the n type doping can have access to the wafer surface only at certain preferred or preferential locations and not everywhere. So, ideally these are the areas. So, this is what you would like to achieve. Okay. So, these are the areas which sort of undergoes a reaction and the doping becomes n type. The areas below this covered zones sort of remain p type. So, in other words, so this becomes n type, this remains p type. The important thing is that when you finally fabricate your IC chip, you also need to remove these covering things, the things you have used for covering. But if you, the one thing you must realize based on the understanding or thing we have discussed so far, that if your n type dopant has to sort of have access to the wafer surface, you also need to get rid of the oxide layer. Otherwise, what will happen if you have a thin oxide layer even over these zones, it will act as a diffusion barrier, and these chemicals which you want them to react on the surface of the wafer for the n type doping will not have direct access to the surface. But the other thing to sort of consider is that if you can have these oxide layer. So, this is the wafer and here you have the oxide layer. If you can do something like you preferentially remove the oxide layer at these areas to have the desired opening, then itself this oxide layer itself can act as that something what we talked here, which is covering parts of the wafer where the chemicals do not have access and they have direct access because the oxide layer is now removed to these parts of the wafer. But here is a problem, I mean when you are actually exposing your wafer to the environment where n type doping reaction is about to take place, an oxide layer, if you remember what we talked a few minutes back, the oxide layer thickness of 1.5 to 2 nanometer is too low to sort of cause any significant barrier. So, the first thing we get started is we deliberately grow on the wafer the thickness of this oxide layer to few microns. So, that and then we do something to actually do this what we have discussed here. We create or preferentially strip off the oxide layer according to the design which we want to create, so that when you have the n type doping, it has access to only these parts of the wafer surface So, the doping, these areas become n type doped, the wafer remains p type doped. So, on the surface you actually have now p n type junctions over here, here, here and here, and then what you need to do is to remove the oxide layer, so that you have a wafer with which now has these p n junctions. Okay. So, in a nutshell, this is what we want to achieve. So, from a flat p, you would like to go to this type of a structure, and that is associated with these individual steps. Okay. So, now if you relook into the animation we had seen a couple of minutes back, I think some of the terms will now make sense to you. So, at least the term, second term, deposition of the barrier layer. So, this is essentially what we mean, that on the wafer which we have taken, we now deliberately grow the oxide layer. Okay. So, it is this particular thing we are talking. So, you essentially grow the oxide layer. Okay. And then so, if you relook at the animation now, so this you should also understand now that you get started with a p type silicon substrate, then you grow the oxide layer on top of that, and then subsequently what you would now try to do, I will come to what this photoresist and all these things, or the what the mask is doing and all these things, but based on whatever little thing we have discussed, our final objective, see what we actually want to do. We are, even if you are not understanding anything of these steps, does not really matter, we will slowly make progress and we will understand each of the steps, but look at something that will make sense to you. And it is this. Yes. So, this is something that should make sense to you now. So, you had taken an oxide layer as we have discussed, and we have now created a pattern on the oxide layer where you sort of see that the n type dopant, which can be phosphorus, has direct access only to the area over here to the surface of the p type doped silicon substrate or the silicon wafer, over which the oxide layer has been preferentially removed. Okay. But now as you see, from point number 2 to this doping stage, there are lot of intermediate steps. So, definitely they sort of help in the achieving the process. So, let us gradually discuss some of them. So, we get started with the process of wafer cleaning. Of course, the wafers are chemically cleaned to remove any particulate matter on the surface, as well as any type of organic, inorganic or metallic impurities. This might sound rather simple, but reality is, in a microelectronic industry, cleaning is a very significant business, because if your initial static wafer is not cleaned, if there are any particulate matter or anything, it is going to spoil your entire chip. Because of the simple fact that we talked that even in a Pentium 2 processor in late 90s, the line width was 350 nanometer. Now, in a i5 core processor, the line width is roughly 30 nanometer. Compared to this, the dimension of a typical dust particle, it is anything between 10 to 50 micron. A human hair, depending on the texture of individual person's hair, the width of a human hair is roughly 50 to 70 micron. So, you can understand that one dust particle sitting on the surface of an wafer is like Mount Everest sitting, and every subsequent process gets completely distorted or damaged because of the presence of dust particle. So, the first step is extremely important, where you achieve the proper cleaning of the wafer. Now, this is what I told you. If I really wanted to give you a detailed description of how industrial it is achieved, there can be anything between 30 to 70 steps involving cleaning of different sorts, different solvent, different types of environment, etc., etc. And in industrial scale, it is fully automatic. I mean, hardly a human hand or intervention of any human being is sort of encouraged. Next thing, once you have the cleaned wafer, is of course you understand that is to develop the barrier formation, or essentially to grow the oxide layer to the desired surface, desired thickness. Oxide layer is very thin, so silica layers Si2 layer is grown on the wafer at this stage. Typically you place your wafer in an oxidizing furnace at high temperature, where there is a reaction of oxygen on the surface of the silicon, and you can lead to the growth of the oxide layer. So, after this you are in a stage like this, you reach this stage. So, you have the wafer and you have the oxide layer. Okay. Now, we have to introduce you, I have to introduce you to another very important term, or a very important item that is necessary or used extensively in the photolithography industry, that is the photoresist. So, the next step is the photoresist application, and the subsequent processes are known as the photoresist processing steps. And which essentially involve the primary steps of dehydration and priming, resist coating, soft baking, exposure, development, and post development inspection. So, all these stages in photolithography or in the flow diagram or flow sheet of photolithography fall under the category of photoresist processing. Now, in order to understand this, the first thing you need to understand or know about what exactly is a photoresist. Well, photoresist is nothing but a special class of photosensitive polymer, and it has primarily two basic functions. It is the material that sort of helps in precise pattern formation. So, if you look here and you now try to get back and correlate to the animation what we saw, our intention is to create something like this. So, you essentially would like to create a sort of a patterned array of the oxide layer on your silicon wafer, like this maybe. Okay. So, these are the areas which remain exposed to the where the p type wafer is exposed to the n type dopant, and other areas are covered with the oxide layer. However, this type of a patterning or direct patterning of the oxide layer is not possible. Direct patterning of layer is not possible. However, what you can do or what is being done, that you start off with a wafer, have the oxide layer, apply this polymer, another thin film of this polymer, photoresist, and this is the addition of knowledge at this stage what you are going to have. We will show you how it is done. It becomes possible to pattern or create regular structures on this photoresist layer. So, you start off with a uniform layer of photoresist, and then you can do something, again I am using the word something, a very vague word, hardly should be used in science, by which you can eventually create domains of the photoresist layer like this. So, these will be sort of stripes of photoresist, and you can do. So, these areas you have the oxide layer is now exposed. So, this is possible to achieve. Now, if you look back at the animation again, probably you will understand our philosophy a little more detail as compared to what you understood so far. So, here you have the oxide layer, now you coat a layer of photoresist So, what is photoresist and what exactly it does we will see. Subsequently, this about this hardware element mask I have not talked about yet. So, you place the mask and whatever these are processing steps I have not, but this whatever you are seeing falls under the photoresist processing steps. But what you now understand is that it becomes possible to create the structures in the photoresist layer. So, earlier we expressed our desire or intention that you effectively want your wafer and on top of that you want to have patterned oxide layer, but we then say that direct patterning of the oxide layer is not possible. So, what you actually, however, what you can achieve is that you can take a photoresist layer, a flat a uniform thick uniform photoresist layer on the oxide layer and then can create structures or patterns within that photoresist layer above the oxide layer. So, this is what you are seeing here, that you now have a structured photoresist layer, and then what you can subsequently do in one of the steps that is written here, we will discuss it when time comes. You can preferentially remove the oxide layer that is below the photoresist layer or the exposed part of the oxide layer. So, if you look at this hand drawn figure, so you start off, or let me draw it again. So, you sort of this is the wafer, this is your oxide layer or the barrier what you have grown, you coat your photoresist, we will be using the acronym PR pretty routinely. Then in the subsequent step you pattern your photoresist layer, you still have the oxide layer and you have the wafer which is let us say p type doped, but subsequently. So, this is PR, the blocks or isolated patches of the photoresist. However, you now have direct access to the oxide layer or only a regular domains of oxide layer which are covered by the photoresist layer are visible. So, in the subsequent step you may want to sort of strip off the oxide layer like this. So, this in principle gives you direct access to the wafer surface. Okay. Now, in the subsequent processing steps, of course, before you plug in your dopant chemical which might actually react with the photoresist layer also, you would like to remove the photoresist layer, and you probably how it is done and all that we will come. So, you have the oxide layer and then you have pass the chemicals for the n type doping. So, these layers, these oxide layers which are now artificially made thick by growing the oxide layer act as barrier over these zones. However, the dopant attacks the surface over these areas and you get p-n type junctions. So, I think schematically or conceptually is it, I hope the what we desire to achieve is clear. So, in order to achieve that we need to have this photoresist layer, first it has to be coated. We also need to understand what exactly is photoresist, though we will not bother too much about its chemistry. We will learn or we will understand that there are two major types of photoresist. Which are known as, some of you might know, if you do a Wikipedia search or search the net, you will immediately get lots of search results. One is known as the positive photoresist and the other one is known, obviously it is easy to guess now, negative resist. Often these positive and negative photoresists are also marked as the tone of the resist. Okay. So, we will understand what it all means, but then comes the question that you need to create these patterns in photoresist. It is easier said than done. Now, what exactly these patterns you are doing? So, if you remember that in our previous lecture we talked about the regimes of top down techniques where you start off with something larger and then at the macro scale maybe you go to a lathe machine and remove some of the materials or do some turning. So, the question to ask is that approach matches, that you start off with a photoresist layer which covers everything, and then you create or take out the material as if one is bound to get a feeling that, well, what ultimately have we done? We have actually removed the materials over here. So, that way it is pretty similar to sort of turning an operation. You start off with a larger material, you remove some of the materials preferentially and create your structures. But I think I mentioned to you in the previous class that the biggest problem or the challenge now is that, if you remember that we are talking about a line width which is let us say 30 nanometer. So, actually what you are doing, that you are taking off material of an area which is only 30 nanometer wide. This can't be achieved with any of your conventional techniques. So, in order to achieve this, and this is going to be very, very regular. So, let us say it is a few centimeter square area over which you are going to now have 30 nanometer lines like this. So, how do you do that? So, it turns out that this operation is done with the help of a hardware element, another hardware element which you just saw in the animation, that is known as the mask. So, what you essentially try to do, this mask is like a original which you want to sort of Xerox. That is precisely the concept that is applied here. So, this photoresist, I will come to the detail, but let me just spend a couple of minutes to give you a very brief idea about the technique. As it turns out from the name, that this is a special class of polymer of photosensitive polymer. So, if you expose it to light, its property changes. We say changes. What does it mean? Well, it can actually sort of, its property can improve, or it can sort of cross link, or its property can degrade. Okay. So, this difference, whether this upon exposure there is an enhancement of the property or the degradation of the property, is actually taken care by the PR or the photoresist tones. So, depending on whether you have a positive photoresist or a negative photoresist, there will be a change of property. The details I will come later at the appropriate moment. But at this time, let us sort of very simply try to explain what it is. So, if you take a photoresist layer on an oxide grown silicon, or it can be any other material, SiW I will be using for earmarking a silicon wafer, and if you expose it to light, what type of light? Typically commercial photoresists work, ideally it can be any light, but these as we will show in one of our subsequent lectures, that these resists sort of show a very preferential absorption peak towards ultraviolet light. Okay. So, if you expose this resist to, let us say, an UV light, then what is going to happen is, depending on its tone, there will be an uniform change in the photoresist property. So, suppose you have a positive resist or a negative resist, I am still not covering that. So, suppose you have a resist which has a property that upon exposure to light it sort of degrades. So, if you expose the photoresist film to UV light, then the whole layer will degrade. In contrast, if you are using a photoresist which has a property that upon exposure to light its properties will enhance, then what will happen? If you expose it to UV light, then the property of the whole layer will enhance. But now, if you can think of a mechanism by which you preferentially expose some parts of this photoresist layer to light and you blind off or blank off some parts. So, what can be a possible mechanism? Suppose you use a hardware piece or hardware element like this. It can be simple slits. So, here you have a slit, okay. So, these are some material is there and in which you have created some slits. Okay. This is just for an example what I am giving, but this actually will give you a very nice idea about how a mask works. So, this is a piece of, let us say, glass or metal or whatever it is, and you have slits. So, if you now suppose if you want to keep this on the surface of the photoresist layer. So, let us say here is my photoresist coated wafer, okay, and on top of that I place this particular block which has, let us say, slits over here, and I expose to UV light. What is going to happen? Let us say that these areas are opaque to UV light. Okay. So, in other words, the light sort of passes only over these areas and nowhere else. Okay. So, only over the slits the light passes. So, what will be the consequence on the photoresist layer? The consequence will be only over the areas where the light has passed, there will be change in photoresist properties. I hope the concept is clear. We talk about a photoresist layer, we understand that it is a special type of a chemical which is photosensitive. So, if you expose it to light which can be UV light, what happens is there is a change in the property. Now, we have not talked about it in details yet, but there can be two types of photoresist tones depending on whether it is a positive resist or a negative resist. If you expose the resist to light, the UV light, there will be a change in the property. So, if the whole photoresist coated film is exposed to UV light, depending on the nature or the tone of the photoresist, either the whole layer will degrade or the whole layer there will be enhancement of properties. Now, what exactly is the enhancement or degradation, we will come into it in greater detail. But if you expose, here is the important thing, if you expose your photoresist layer to UV light, then whatever is the change in the optical property that will occur across the entire zone or the entire film. Now, if you take a simple hardware piece, a commercial mask is not exactly like this, but for our understanding, let us say that we take a piece of opaque material and we create slits opaque to UV light or the light you are exposing for photolithography. So, these areas it is opaque, and the other areas it is transparent. So, if you now place this hardware piece between your UV light source and the photoresist layer, then what is going to happen is that UV light can pass only over these areas, okay, and it cannot pass over these areas. So, it is going to sort of have some hindrance in its path, and the photoresist layer below, which can be placed right on the photoresist film, the photoresist layer below this hardware piece will get exposed, but only these areas which were below each one of these slits will be exposed to UV and undergo a change in the property. So, now even on the uniform photoresist layer, there will be domains which now have different chemical property and this difference in property is due to preferential exposure to light or UV. So, this is important, and for all practical purpose this hardware piece is what is known as the photolithography mask. Okay. So, here we add a little more to the story now. You have a photoresist coated layer, then what you do, you place a mask. Okay. So, this is the mask. Let us say these are the opaque domains and these are the transparent domains. Now, you expose light, expose it to UV light. So, what is going to happen? These areas of the photoresist layer which fall below the transparent domain will undergo some change in their optical properties, or will undergo some change due to their exposure to UV light, and you know these are photoresists. So, these are photosensitive material. So, because of that photosensitivity there will be some change, and now when you remove the mask you still have an intact photoresist layer on an oxide layer, but you already have created domains within that photoresist layer which are exhibiting different property as compared to other areas, or you have domains corresponding to the design of the mask and which has been subjected to UV light. So, essentially you create your original pattern on the mask and that preferentially gets transferred onto the photoresist layer. So, before I stop this class, let us have a quick look again at the animation. So, this you understand now, oxide layer, this you also understand, we now apply a photoresist layer. We now understand this, we have a mask here and this mask has a special feature. So, let us say it allows transferring of light only over these areas and other areas it is opaque, or it can be opaque over these areas and other areas it is transparent. You place this mask on the photoresist layer and now you expose it with UV. So, depending on the type of mask, the areas which were sort of transparent, there is a change in the property of the photoresist layer. We will pick up the story from on further discussion on photolithography from this point in our next class.